All right. It's 5:51, so I'm gonna get started. So today's lecture, I think some of you will like it because you guys are getting a gift that no other students from past semesters has. Because I just finished making a tool to help you debug your program. Yeah. Okay, so I'll talk about that a little bit. Um, and then we'll also start to talk about how to compile a program that is written in C and into the assembly code that we are used to. Okay? Yep.
Will you show us how to take the data from registry and put it back to RAM?
There's only one instruction to do that. It's called the store instruction, the ST instruction. Yep. All right, so we can talk about that too, but that's just one single instruction that does that. Okay, all right. So first thing first, I'm going to show you the tool that I just made today. But in order to use that tool, you have to download the processor file again, because I made some changes, so you have to download it again. All right, but I also made some changes to the assembler manual, so maybe I will start with that one. So if you go to the assembler manual, I hope many of you have at least taken a look at this manual, okay? Because you are using that assembler, so understanding the syntax and how it works can be quite useful. So if you scroll all the way down to how to debug here, that's basically the instruction, okay? Don't worry about all these being so wordy. I will show you how to get it done. Yes? I believe so. The recorder is on, and let me see, where's my streamer? I don't know where it puts it, but I think it's on. I can check it on my phone, You guys cannot check it because it's not public until I release it, but I can check it on the phone because it is should be showing up here now. Let's see. That's my previous class. Interesting. So when it is being streamed, it doesn't show up on my end either. Let me see if I can find it. Yep. So it is streaming, and we can see that it's using about 2 kilobits per second, so it's not really using a lot of bandwidth. So if your game is lagging, it's not because of me. All right. So we'll talk about this, and I will talk about how to use it. Yep. The podium. It may not be that light. Okay. Yeah. Thank you. I mean, who uses a podium these days? And where's the teleprompter? Because usually, that's one thing that I learned is, how come all the politicians know exactly what to say, when they have like super long speeches to begin with, right? And as it turns out, they got teleprompters. Newscasters too. Sometimes you can see their eyes just kind of like, shifting when they're reading the teleprompter. So that's why. That's how they do it. Okay, so we'll talk about this, and I will show you how it is done. For some of you, you may not be comfortable with the command line stuff. But it's not really a whole lot of command line stuff. It's just one command, and once you get used to it, it's not too bad. Okay, but in exchange, you actually get to know a lot about how the processor works as it executes your program. So that's going to be useful. But before you do that, okay, so I'm going to a folder, and I think I have a processor folder already, because I just want to keep everything into a particular folder. So I'm making a new folder called processor. And just to be sure, you probably want to download all the files again. So what we'll be doing is we are re-downloading processor 0003.circ, register bank, and ALU. ALU has not been changed, but just might as well do it. Okay, so download all three of these. Okay. Okay, so we got the files. The zip file, where I put a zip file doesn't really matter because it's where I zip it, unzip it to that is important. So I'm going to go to my processor folder. Okay, so you can see better. Is that okay? Is it big enough? Okay, all right. So I just unzip whatever the folder is. There we go. And then we'll go ahead and get a program, okay? So you have to have a program to run to actually see the way how it works. So I have a program already in my assembler tab. Okay, so this is the program that we talked about last time. Remember this program? Its only purpose is to illustrate how JCI operates, right? I hope you guys still remember. It was only Tuesday when we talked about this. Yes? Okay, so this is a continuation, okay? This is great because now I can actually show you how we can visualize the execution of this program, using a table. So we'll keep this program. As usual, we go to the RAM file tab, go to File, and then we say Download as CSV or TSV, it doesn't matter which one in this case. I'll just call this test.tsv. There we go. And then switch back to the assembler. And of course, there's a long command you have to type. So the long command you have to type is java-jar. So if you have been using the exe version of Logisim, you have to go download the jar version. Okay, the jar version is what they call the generic version because as long as you have Java installed, you can always just do it on the command line. The exe version actually has the jar file built into it, but except it is kind of pre-packaged together. So do it this way, and then go locate where you have downloaded Logisim, and I have to find mine. Uh-oh. May not have mine around. Okay, I don't have mine. Let me see if I can find it. Yep, I do have it. So java-jar, and then wherever you have your Logisim downloaded, the jar file. So mine is located here. And then the name of the main file, which is processor 0003.circ. Now this command is already documented in the assembler manual, so you don't have to copy this, okay? You just kind of have to focus on what components I have to specify. So if you do it this way and press the Enter key, it just brings up Logisim, the usual graphical user interface. So this is not what we want, okay? We want things to be a lot easier than this. So what we do is now we specify additional arguments. One is load, okay? So dash load, and then you specify where the CSV file is located. I put mine into the temp folder. Typically, most people put it or keep it in the downloads folder. So that's where you will find yours, okay? The tilde symbol may or may not work in Windows. I believe it does not work in Windows. So you kind of have to figure out how to do that in Windows. Okay, so next we have to specify that we want this to be using the TTY or teletype interface. So instead of starting up the GUI, it is going to use the TTY or the teletype or standard out from your perspective, okay? And then you specify table, so it cranks out the table. That's it, okay? So we'll just keep this much for now. Press the Enter key, and this is what it gives you. What does it mean? Well, these are all the output pins. So every output pin in processor 0003.circ, it has a column as an output. But if I want you to look at this and go like, oh, tell me where the program counter has been, okay? It might be a little bit difficult, right? Okay? So what you do now is to repeat the previous command and then use the redirect symbol, which is the greater than symbol, and then you put it into a file, okay? I'm just going to put it into a file called log.tsv. The name doesn't really matter because when you upload to Google Spreadsheet, the extension really does not suggest how to open the file. So you can use txt if you want to. So this is a tab separated value file. And so now this time the command line does not give me any output because the output is redirected to the file. It is being stored in the file. So what that means is if you want to look at a file using a notepad, you can actually do that. It's not going to be very helpful because it just looks like that. Okay, you don't even know which column is which column. So what I did right before this class was I made a tool to make it easier so that you can process this or gain an insight of the execution of the program kind of more easily. So you go back to the processor folder. There's a new file called trace analyzer, which is down here. So once again, this is my version. If you want to use it as your tool, you will have to make a copy into your Google Drive first. Okay, just like with the assembler, you have to make a copy that is your own, because otherwise you cannot change it, right? And I don't think it will work in an Excel environment, so don't download it and reopen it using a spreadsheet program. That probably will not work, okay? And I know this is not going to stop you guys. Some of you will try to do it anyway. So it's okay. Nothing's going to explode. It's just not going to work. All right, so go into this spreadsheet. So this spreadsheet so far only has sheet 1 and sheet 2. So stay on sheet 1 and go to the cell A1, but don't double click it. Just make sure that it is selected. Then what you do is you go to File, you go to Import. Okay, once you get to Import, you can go to Upload and select a file. So in this case, it is called log.tsv, which is here. Click Open. Then it will ask you a bunch of questions. Now, this is where you have to be careful, slow down, make sure you select the correct ones, because otherwise it won't work. So you have to make sure that you replace the current sheet, but not the entire spreadsheet. Because if you replace the entire spreadsheet, the other sheet that is useful will be gone too. So only replace the current sheet. And then you want to select tab separated. I think detect automatically would work too, but I always make sure that it uses tab as a separator. And then the last one is also important. Do not convert text to numbers, dates, and formulas. The problem with that conversion is some of the numbers can convert, some of those cannot convert. So you end up with some kind of mismatch of stuff. So just do not do any conversion because my script or my formulae will do all the conversion for you. And then you click Import Data, okay? And it gives you this, this is, I guess I was using the same log file when I was home, so that's why it didn't seem to change. Then you go to Sheet 2, and this is the interpreted version in hexadecimal. And it also has the header column to help you understand, which column is register A? Which column is the program counter? Which column tells me that I'm accessing RAM? So you know that you're accessing RAM when RAM select is a 1, okay? But when you're accessing RAM, am I reading from RAM or am I writing to RAM? So now RAM load will tell you, because if you have a 1 here and a 1 here, you're reading from RAM. If you have a 1 here but a 0 here, then you have a write operation. So far, we don't have any programs that writes to RAM. So at this point, we don't have anything that will show you, this is a RAM overwrite operation, which relates to your question earlier, because we don't have any program yet using the ST instruction. So are we doing okay so far? Okay. OP fetch can be useful because when OP fetch is a 1, it means it is the fetch cycle. We are getting the opcode. Okay, so that can be useful to help you distinguish, are we getting something as data or am I getting something to execute? Am I getting the opcode or am I getting some data to process? So you can now differentiate between those. Are we good so far? Is that good? Okay. So you can take this spreadsheet and extend it further, right? Because what you can do later on especially, oh, by the way, data is really just the data bus, okay? This is what we can observe on the data port, okay? And then address is whatever is presented to the address port of RAM. So by combining data, address, RAM select, RAM load, okay, you can then figure out, am I reading, am I writing, am I executing something, and where am I reading from? Where am I writing to? So you can reconstitute the content of RAM by analyzing this trace. We don't have any need to do it just yet. But later on, when we start to talk about the stack and stuff like that, that becomes really useful. Do we have any questions at this point? No questions? Okay, all right. So we'll just kind of, let this one, sit for a while, as we talk about other topics, and then we'll come back and look at this one when it is time to do it. But I'm telling you, in all past semesters, students did not have this tool, so they would have to analyze everything kind of manually, and then every time they do the trace, they have to kind of run it and set up everything by hand. But now you don't have to do it because it's all done automatically. Are we good so far? Okay. And I know a few people are always going after efficiency. So for those of you who are really after efficiency, you can, okay, let me go to here. Okay, so this is module 0325. If you know how to get to one of my modules, just change the module number to 0325 and you will get to this one. So this one is really cool. It gives you the basic idea of how to use a command line script written in Node, JavaScript, to interact with a Google spreadsheet. Why would you want to do that? Because this way you can directly interact. So you can take the source code from a file, upload it using the command line to the source tab of the assembler, and then download everything from the RAM file, stick it into a file, run Logisim using the command line, collect the output from running Logisim as a tab-separated file, re-upload that to the trace analyzer, re-download the trace analyzer sheet 2, and you just have one command, right? And then everything is done automatically. I haven't really gone to the extent of doing this yet. I'm only showing you that it is possible. It can be done. Is that okay? I don't know how many of you have the time, to kind of look into this sort of thing. But it is going to be helpful, okay? This is the kind of thing that employers look for too. So if you have spare time, to look into something like this, it can be helpful. Okay, so there is that. All right, so we are back to. Nope, this is the wrong one. Okay, let me go back to the sign-on page. Go back to this class. And we are right here. Okay, so this is a very short description of what I just demonstrated. So if you just need a quick reminder of how to do it, that page can do it. And this is our lab for today, or for tonight. So we'll get to that later, because I can't talk about it until I finish this particular module. So we get to this module, and this is what I was talking about. See how this module is 0303. If you change this 0303 to 0325, you'll get back to the other module. So that's just a quick and easy way to switch between the modules. All right. So last time we basically talked about the conditional statement, how we convert a structured conditional statement into something that is not structured. The reason why we want to do this is because in assembly language, we only have conditional branch instructions. Now, I understand, okay, this particular C, condition C here, may not be a very simple condition. It can be a conjunction of some disjunction that involves negation in the inside, or even calling a subroutine or something like that, okay? I understand that. But we'll have other steps to boil down a complex condition into simpler conditions. So don't worry about that part. But the most important part is eventually this condition is going to be a comparison. Is x less than y? Okay? Does x equal to y? Is x greater than y? That sort of thing. So that is why it is important to boil everything down to that point, because we got JLI to say that if the first operand is less than the second operand of the previous compare instruction, go to that location. We got that. We got JZI, which means if the first and the second operand are the same in the previous compare instruction, go to that label. Okay? We got JCI as well, which is kind of the same thing as JLI, except one works for unsigned interpretation and the other one works for signed interpretation. So that's why we want to boil everything down to this particular format. The goto is not a problem, okay? We have goto in C and C++, but we have JMPI in the assembly programming language. So goto is not a problem. Labels, not a problem. This is the proper syntax of labels in C and C++, C and C++, but we have the same thing in the assembler. So we don't have a problem with that either. Are we okay so far? Do we understand why we are doing this conversion? Okay, all right, excellent. So if I remember correctly, we did the pre-checking already, and post-checking was not done, okay? But post-checking is relatively rare. We usually use pre-checking loops in most programs, but might as well just talk about it too. So if your post-checking loop in C is do and then some kind of block 1, okay? Now block 1 doesn't have to be one single statement. It can be a bunch of statements, okay? The whole idea is it is a block. While C, it translates to label L1 so that we can go back to the point right at where block 1 starts, and then perform block 1 first, because this is a post-checking loop. We perform the operation first, and then if C is true, then we go back to L1 to perform another iteration. So can everybody see how the structured version, which is the top one, and the unstructured version, which is the bottom one, they are functionally the same. One looks ugly, but the other one is, hey, it gets the job done even though it's not structured. Are we okay with this? Yes? Okay? All right. So with this out of the way, then we go to conditional branch instructions and go like, well, what about the negation? Can we get rid of the negation? If you see something like this, if not C, go to L1, which happens quite a bit, you can convert it to if C, go to L2, which continues, and then go to L1 if C is false. Is that okay? We are sacrificing statements in order to simplify the expression. Is that okay? Now, don't do this unless it is necessary, okay? Because there are many other ways to get rid of negation. So depending on where you encounter the negation, you may not have to do this trick. The next one is or. If the original statement is if condition C or condition D go to L1, which means if C is true, I go to L1 right away. Well, if C is false, then I check D. If D is true, then I also go to L1. Is that okay? That's what the original statement says. So in order to get rid of the logical OR operator, because we don't have a logical OR operator in assembly language programming, then what we do is we just break it up into two go-to statements. If condition C is true, go straight to L1. Don't even bother to check D. Okay? If C is false, then we are not going to L1. Well, then we check D. If D is true, then we still go to L1. If C and D are both false, then we fall through the entire thing and just continue execution with whatever is next. Yes? Oh, the not thing? It's, I mean, you can get it all from the notes too, I mean, yeah. So now we have the AND, okay? So if C and D go to L1, what does that mean? That means if C is false, don't bother to go anywhere, just continue. Well, if C is true, then we also want to check D because we need both C and D being true in order to go to L1. That's the meaning in C and C++ for that particular statement. So if we want to get rid of the AND, then we have to break it down into something like this. If C is false, go straight to L2, which is a continuation label, which basically says, no, there's no chance we're going to L1 if C is false. If C is true, then we are not going to go to L2 right away. We're going to check D. If C is true, then we go to the next conditional statement. If D is also true, then we go to label L1.
Where's label L1?
Huh?
Where's label L1?
We don't know. We don't care. Somewhere. All I really care is, does this statement do exactly the same thing as what this other statement does? And if they do exactly the same thing, I don't really care where L1 is. Because L1 is generated by some of the earlier constructs that we have talked about. So are we good so far? Well, we have just talked about the 3 techniques. So if you apply these techniques repeatedly, eventually you will boil down everything to just comparisons. Does that make sense? Okay, or function calls, but we won't deal with function calls until much later. So now we talk about simple reductions. So if your negation applies to a comparison, then you can just use tricks to convert it so that you don't have to end up using complex logic to do it. Does it make sense? So if your negation is applied to x is greater than or equal to y, then you just look at that expression and go like, we don't really need that negation. We can just say, is x less than y? Does that make sense? Is that okay? All right, cool. If you have something that looks like this, if x is less than y or x is greater than y, that really is just asking, is x different from y? So you can do reduction sometimes based on algebra, when you're comparing. Yes? That's later. Yeah, when we get to that last point, then we'll get to that. Okay. Do we have any questions about simple reductions? Section 4.4. No questions? All right. So now we are moving down to comparisons. Okay. Now this is something that we have seen already. We only need less than. We have talked about this, I think, some time ago. Okay, some of you remember that. So if we can only have less than, how do we implement less than and also equal to? We can also perform equal to. So what do we do with something that is not less than? Well, greater than is easy. You just switch the order. If I'm asking you, is x greater than y? Well, you can just translate that question to, is y less than x? Okay? X is less than or equal to y. It can become x is less than y or x equals to y. We can do both because we have the JLI and JCI for less than, and then we have the JZI for equal to. So the right-hand side is something that we can easily do. Is x greater than or equal to y? Flip the x and the y for the less than, and then we check for equality. Does x equal to y? Oh, that's easy. JZI can do it. Is x not equal to y? Then you have to negate x equal to y. We can negate it. There are several ways to negate it. One method is something that we talked about earlier. Is that okay? And for those of you who forgot, this is logical negation. The same thing as an exclamation point. Is that okay? Are we still doing okay so far? So a lot of this is pretty mechanical stuff, but I do want to spell out the more mechanical stuff, just so that we don't have a problem with that. So now we are dealing with compare. So this r is less than or equal to. So this r, lowercase r within the expression can be less than, can be equal to. So the question is, if I boil everything down to if x some relationship with y go to L1, how does that translate into assembly code? Well, it just translates to this. This is JRI, by the way. You need an I. So you compare x to y. X has to be the first, y has to be the second. And then JRI, okay, is J either ZI, CI, or LI, depending on whether you want to know whether x is less than y signed, less than y unsigned, or equal to y. Okay? It's just a template. So here's an example. If this is the statement I want to implement in assembly, if x is less than y, go to L1, then it translates to compare xy first, then JCI L1. Do we have any questions about that translation? No translation, no question about that? Okay. The last point is the toy processor can only compare registers, so the CMP instruction cannot compare to constants. So I cannot compare to, let's say, 5 or 10 or 1. So that means if you want to compare against a constant, you have to use LDI first to load that constant into a register and then compare to that register. Okay? This is one of the disadvantages of using a RISC processor because with a CISC processor you can just compare to a constant. But with a RISC processor you have to do one extra step in order to compare to a constant. Yes? Huh? Yeah, so all of the operations can only operate on registers. The only thing you can do with constants is LDI. That's the only time you can specify just a constant is LDI. All right. So now we have to deal with nesting. So now we have to deal with nesting. So nesting involves, so I'm going to skip a little bit here. So let's look at this code here. So we're just trying to translate this code into assembly. So what you need to do is to have, this is not too bad because we only have a while on the outside and a conditional statement in the inside. So if you just kind of prefix your labels with while and if, you'll be fine, okay? But what if we have a while loop inside another while loop? Then we have a problem, right? Because if you just use label names like L0, L1, and so on, it is awfully confusing, okay? And before long, you'll be using the wrong label and your program doesn't work because it's branching to the wrong point. So now the question is, how do we systematically label all the points within the control structure so that we don't have that problem to begin with? So we can use the suffix or prefix method. So in this case, it translates to this. Okay, this is the original code, and it translates to this part here. It represents the same logic, it just looks different. Is that okay or not? We good? And then we work on Boolean operator reduction, which basically has to do with, you can use a suffix to deal with that too. So in this case, because we have to use another label, so we just use a suffix of _1 to represent that extra label that is generated. So every time you have to generate an extra label, you just do an additional underscore to whatever you have originally, then you won't have a collision. In other words, this is my recommended way to mechanically generate label names so that you won't run into the problem of, oh, which label am I supposed to use here? Okay? If you have your own method that works well for yourself, use that method. I'm just pointing out that you might run into issues of, hey, which label goes where? Okay? So we have a long example here, which you guys would probably like. So do you want me to go over this, or do you want to? Okay. Well, the rest of this module actually goes over that, step by step too. So it's not like I give you the final solution in one step. I actually do it step by step. So I don't know whether you guys want me to just to read this or do it, actually in Notepad. Let's do it on Notepad. Okay, so what we'll do is we're assuming x, y, and z are somewhere, okay, probably in registers, so that we don't have to worry about that problem. And then we just put it into mousepad. So you probably don't want to spend too much time actually writing this down, because that's going to be counterproductive if you spend too much time to kind of try to copy everything. So the first thing we do is we look at this and we want to flatten it. Okay, in other words, it will still be C code, except it's not structured anymore. But I don't deal with many items at the same time. I only deal with one item at a time, one control structure at a time. Okay. So to use the suffix method, I would probably go from the outside in. So I would deal with this while loop first. Okay? So to deal with that while loop, I'm going to comment out the original code corresponding to the while control structure, and then I will replace it with the flattened code. The flattened code is basically saying, okay, we have a while begin label here, and you can always append it with a 1, 2, or so on, in case you have successive while loops, like this is followed by another while loop, then you have while 1, while 2, and so on. So you can say while 1 begin. See, even though we only have one while loop, so that's not necessary. So this is a begin, and then at the end of the entire block, we have to go back to the beginning. So we know that we need to go to here to while 1 begin. Is that okay? That makes a loop, a jump at the very end to the beginning. But the while loop knows when to exit as well. So now we have to say, if x is less than or equal to 0, then we want to go to another label, which is while 1 end. And then while 1 end is going to be right here. Okay, let's just kind of stop here. Do we have any questions? Are we good so far? Yes? We good? Okay. Are we okay? All right. So with this done, then our focus is now going into what is inside the loop, which is another loop. So now we're dealing with this part of the program. We have already flattened the outside, and now we have to deal with the inside. Now the other thing we can also do, because of the flattening, is this pair of curly braces is not needed anymore. Yep. Okay, so that one, this is matching that beginning. So that pair of curly braces are not needed anymore. X equal to 0, we don't worry about that. It's not structural. This while loop is structural. This is our second or nested while loop. So what we want to do now is we comment out this one and its corresponding end, and also the open curly brace corresponding to the beginning. And then we do the same trick, except we have to be careful with the label. Because at this point, I don't want to call this while 1. It is the while 1 inside the while 1. Is that okay? But it is also the begin label of that while 1 inside the while 1. So this is while 1 begin. And then we go to the end here, and we say we have to go back to the beginning at this point. Okay. So we say go to while 1 underscore while 1 begin, like so. But this loop, the inner loop, also needs to specify when it should exit. When should we exit? Tell me. The condition to stay in the loop is when y is less than 5. So when do we exit? Greater than or equal to 5. Very good. So now we say if y is greater than or equal to 5, go to while 1 end. And then we define that right after the go to. Well, we can put it here. While one, and goes here. Are we good so far? Yep.
My question is kind of related to line 13.
Mm-hmm.
Do you not want to put if 5 is less than y? Am I thinking
Well,
about
if y is less than 5, we stay in the loop. It's when y is greater than or equal to 5 that we exit the loop. Then we go to the end label of the loop, which represents we are now out of the loop. Because you can see how the while one end, sounds like a movie, is right here, which is right after the go to. So it's outside of the loop. Yep. Question?
Never mind, actually, answer my own question.
Okay, those are the best questions. And the answer is the best too. Because if I answer the question, it won't sink in as much. If you are answering your own question, that is yours now. No one can take that answer away from you. All right, so if we are okay with this, then we only have one more control structure to deal with, which is this conditional statement. So this conditional statement is a little bit on the nasty side, right? Because it has a and that is inside the or, okay? Well, let's do this. So what we'll do is we comment out the structured code, just like usual. Okay, so we have to remember to also comment out the end curly brace corresponding to the control structure that we are working on. So now we replace it. And then we say if it is not the case, and I'm going to be very lazy here. If it is not this, then we go to, how should we call that label? While one, if one, end. But you can see there is a structure. There's a particular way that I name these labels. They are just they're just becoming longer and longer and longer. Okay, so while one, if one, end is going to be defined here. Because it is telling me where is the end of the conditional statement that is inside the first loop, inside the first loop. That's what it's saying. Is that okay? So are we doing okay so far with this translation up to this point? Are we good? Do we still have curly braces? Have I commented out every single curly brace in this program? Not counting, main, but in terms of just the statements, have we commented out all of the curly braces? Well, that means the program is no longer structured, okay? Because your curly braces or the use of block statements is an indication that you're using structured programming techniques. So we are doing exactly the opposite of what you have been taught to do since cisp310, which is to write programs in a structured way. We have just disassembled the structure. So the program is now flat. There's no structure to it. But we still have a problem, because we have this problem of, hey, we got a negation on top of this complicated thing, and there's no way I can translate this into assembly code like just 2 lines. So what do we do about this? There are 2 ways you can fix this problem, okay? The first one is to look up the notes here, and you ask, oh, we have the negation of something. You can apply that rule. The second thing is a little bit trickier. You basically apply what we call De Morgan's law. In other words, you use Boolean algebra to simplify the expression instead of using control structure to simplify the expression. Are we good so far? So do you guys still remember what is De Morgan's law? Did you guys study? Yeah, something like that. So, so I'm going to explain what is De Morgan's law, okay? One more time. Okay, so De Morgan's law says, the negation of A and B is really exactly the same thing as not A or not B. That's one part of De Morgan's law. The other one says the negation of A or B is really the same thing as not A and not B. That is De Morgan's law. Very, very useful, when you are going into computer engineering. Okay? In computer science, it's still really useful, kind of helpful in many ways, but not as useful as when you're getting into computer engineering. So are we good so far? Do we understand what is De Morgan's law? Yes? One spells as S-C-I-E-N-C-E, and the other one spells as E-N-G-I-N-E-E-R-I-N-G. The difference depends on the university. It depends on what they put into that particular bachelor's degree. At Davis, it gets even more confusing because they have a computer science degree, they have a computer science and engineering degree, they have a computer engineering degree, and then they have an electrical engineering degree. Yes, computer science and engineering is in the College of Science, I think. Engineering.
Computer science is in the one with economics. It's in the same college. Yeah. Colleges of Letters and Science, and then computer science and engineering is in the engineering.
So computer science is no longer in engineering.
I think it's always in
It's in the College of Letters and Science.
Okay.
I have no idea.
Then they changed from my days. Are they still across the hallway from each other?
Probably. Like, it's basically the same thing.
Okay. So does that answer your question? In some universities, they don't have computer engineering as a degree. It is always computer science and engineering. So, it just comes in a whole variety of combinations. In the end, it doesn't really matter. Okay, you can be a computer science, student, or you can graduate with a computer science degree, and then you cross over on your own and become a computer or even electrical engineer. Or you can graduate with an electrical engineering degree and then cross over on your own to become a computer science person. Okay, so, it doesn't matter that much.
Computer science guys are not engineers.
That is correct. So, especially at UC Davis, any engineering degree will take 5 years to complete, where most degrees will only need 4 years. So, not being in engineering, saves that 1 year. All right. But then you don't get to, take all the cool classes like control theory and whatnot. Okay, so now we get to this part here, and it is about changing this expression to the point where we can easily deal with it. Okay, so what we'll do is we're going to copy and paste it. Copy, paste, comment out. Okay, so what we'll do is we'll apply De Morgan's law, which basically takes this negation out and then apply that to the inside of that negation. And then in the process, we also have to change the or into an and. Is that okay? Are we feeling okay with this? Okay. Yeah, I'm just making sure that the parentheses are still correct. Yep, we're good. Okay. So at this time, I'm going to do one simplification, which is taking this negation, whoops, where's my select? There we go. And just move it inside here. It is not the case that y equals to 1. It's the same thing as x does not equal to 1, okay? It's just kind of easier the way to say it. Okay, but we still have a negation on the outside of this conjunction. Let's get rid of that. So now we take this negation, okay, take it away, move it inside. So now you have to do it, okay. So we put one here, we put one here, and then we turn this into an or. That is how you apply De Morgan's law. Then you look at this and go like, well, I think there are better ways to say that, because not that x is less than 2 is the same thing as x is less than or equal to 2. Take away that negation. Not x does not equal to y, I think it is the same thing as just x equals to y. Is that okay? So now it's the same thing as what we had originally. It just looks a little bit cleaner now. So are we good so far? So at this point, I can use distribution and some other crazy stuff, but it's not going to really help me all that much. So it's time to really use control structure, like do more work with the conditional branch in order to get rid of the conjunction first. Okay, so now we comment this out, and then we apply what we learned a little bit earlier. Okay, and we say that if it is not the first condition, go to while one, if one, and underscore 1, which is the continuation label down here. So we have while one, if one, and underscore 1 defined here. And then the other one is the confirmation. If blah, blah, go to where we want to go in the first place. Okay, this is what we learned a little bit earlier. Let me show you where we learned this one. Let's see. We talked about this in the conjunction one. I'm sorry about all that scrolling. There we go. Because we have conjunction as the last operation earlier, so we break it up into 2 conditional statements with 1 additional label, so we can use that as a continuation label. The first condition has to be negated in order to branch to the continuation label. The second condition is not negated because that confirms that we can in fact go to label L1. So using that particular template on the program that we're working on, so what we do is we now take this part here, which is the left-hand side of the conjunction, into this negation. And then we take the second part of the conjunction and put it into the second conditional statement here. Question? Yes?
Wouldn't you have to put the while one, if one, and one after the statement that's executed within the conditional block?
On which line?
Or am I reading that wrong? On line 22, you have the statement that's executed inside the conditional block.
Yes.
So
Because it's a continuation.
Oh, okay.
Yeah. It's a continuation because this particular goto is going around the if. In other words, if the original statement is false, we want to end up here. So let's think about it. Okay, let's just think about it a little bit here. This statement, which we have commented out already, says if at least one of these 2 conditions is true, we want to execute z gets z plus x, right? So what we end up here is if we can show that if it is not the case that x is less than or equal to 2 or x equals to y, then we can go to this part and execute z gets z plus x, which is correct because the original statement says this is a conjunction, but it spells out the same thing as this one here. If x is greater than 2 and x does not equal to y, so this basically says if x is less than or equal to 2 or x equals to y, if it is not the case, right? So it really spells out exactly the same thing as the original one. Mm-hmm. But the way I'm doing it is actually mechanical, even though it's really messy, but each time for each step, I'm only mechanically applying one of the steps that I have mentioned. Okay? So this one doesn't need a whole lot of attention any further because we just want to confirm that y is not 1, so there's nothing to really work on in this case. This is the one that we still have some work to deal with, right? Because we have an or, and we have a negation. So with a negation and an or, the first thing you want to do is to distribute the negation using De Morgan's law into the inside here. So we put this negation here, and then we put another negation here, and turn this into a conjunction. That's the application of De Morgan's law. Yes? Oh, okay. And after that, there's nothing we can do here. So we'll have to go to, we have to use the conjunction thing again. So to use the conjunction thing again, this means that we have if the negation of the first condition go to a continuation label. So this one is going to be while one, and if one, and underscore one, underscore one. Because it's a new label, it's a new continuation label. Every time you need a new continuation label, you append underscore one, so that we do not accidentally use something that is already used. So that continuation is going to be here. While one, underscore while one, underscore if one, and underscore one, colon. And then the next one is a confirmation to actually go to the original label, which is now while one, if one, and underscore one. Are we good so far? This label is the same thing as where we wanted to go in the first place. Whereas this label with an additional underscore one is a branch around the label. It is a continuation label. So now we just have to populate the conditions. The first condition, which is this entire thing, including the negation, goes to here. The second condition, including the negation, goes to here. Yep. Yep. Well, yeah. So right now we can do some simplifications. So the double negation is canceled out. We don't need the extra parentheses. This one, is just the negation of an equal. So we can just say not equal to, and then get rid of the unnecessary parentheses. And now we're good. So now we have translated this program into every condition only involves a single comparison. Are we good so far? Yes? So do you guys want to break this program all the way down to assembly instructions? Okay, let's do that. Now, to do this part, we have to make an assumption that x, y, and z are all in registers. All the variables are in registers. So we have 3 variables, x, y, and z, and they're all in registers. So now we comment out this one and say, okay, we want to initialize register x with a constant of 5. That's the job of LDI. Okay. Z needs to be 0. Okay, kind of the same deal. LDI z 0. Now, we do not have a register x, y, or z, okay? So I'm just saying that if variables x, y, and z are all in registers, this is what we can do with that, okay? But if they're not in registers, they're in memory somewhere else, then we have to do some other things. All right, so let's deal with this one first. Okay, this is the step where we have to translate a C, the last level of C control structure to assembly code, okay? If x is less than or equal to 0, go to while n. How am I going to do that? Well, fortunately, we have 4 registers, so we have one other register, let's say register D, that we can use for constants. So we load D with a 0, and then we do a compare of x to D. Remember, D has the content of 0, so that would do the comparison. It says, if it is less than or equal to, so that means, well, okay, are they signed or not? Let's check. Signed. Okay, so if they're signed, we use JLI to while end, and we don't forget that we need the other one too. Do we all understand why we have both JLI and JZI? JLI takes care of the less than, JZI takes care of the equal to. So if it's less than or equal to 0, we branch to while end. Are we doing okay so far? Okay. So now we move in. Okay, y is 0. That's easy. LDI y 0. Once again, we are assuming y is in a register already. So we don't. So in the actual program, we have to translate x, y, and z into registers A, B, and C. Yep.
13 and 14, is it while n or while 1?
Oh, it's y1. Thank you. Good job. All right, so moving on, we have this label. Label definitions can stay exactly the same way as they are, okay? There's no problem with that. All right, so now we have to translate this one. If y is greater than or equal to 5, go to this particular label. So we need LDI again, because once again, we cannot compare to a constant. So whatever constant we compare to, we have to put it into a register first. So in this case, how would you do this? There are several ways to do this particular one. I just want to see how you want to do it. We can flip the order. We can compare the 5 to the y and then just use the same trick, JLI and then the JZI. That works too. We can also, do the other way. We can say, if y is less than 5, go around, and then, go to y1, y1 end. So there are two ways to implement this particular one. Flipping it would be easier? Okay, we can flip. So we now compare D to Y, flipping the order. So we now say if JLI to while1 underscore while1 end, and then we have JZI to the same label. Are we good? All right, so now we have this one to deal with. Comparing to 2, so we have a LDI D with 2, and then we do a CMP XD. Once again, we have JLI to while1 if 1 and underscore 1 underscore 1, and then a JZI to the same label, like so. So now we got this taken care of. Okay. And then we have if not equal to. How do we do that? How do we implement line 36? Well, you can do it in several ways, okay? So for this one, I'm going to have to do it kind of take out the negation. So I'll do it one more time, okay? So I'm going to say if x does equal to y, go to while1 underscore if 1 and underscore 1 underscore 2. I think, we used the underscore 1 already. And then the next one is an unconditional go to the original label, like so. And then the 2 is defined here, while1, if 1, and underscore 1 underscore 2 is defined here. Is that okay? The reason why I use this particular technique is because we can check for equality pretty easily, because that's just a JZI. So we have a compare XY, and then JZI to while1, if 1, and underscore 1 underscore 2. Okay? And then this particular go-to, which is an unconditional branch, is just replacing the go-to with a JMPI. So this becomes just a JMPI to while1, if 1, and underscore 1. Is that okay? So we have two label definitions, and then we have a compare to 1, and we're looking for not equal to. So we need a LDI D with 1 because we can only compare between registers. And then we use the same trick, compare Y to D, and then we have a JZI. Well, the reason why we can only use JZI is because we do not have a NZI. So there's no conditional branch just for when the 0 flag is not a 1. Okay. So this will have to go to while1, if 1, and underscore 2 because it has to be a new label. And then we have an unconditional branch to while1, if one, end. And then we define the continuation label here. There we go. This one is easy. We're just adding x to z. That would do it. And then this go to just needs to be changed to JMPI. Like so. And then this go to just needs to convert to JMPI2. And we're done. This is why we have compilers. Because what I have just done is what the compiler do. Yep.
So in generic assemblers, do they have similar naming conventions, or do they use for labels, or do they use tools to circumvent this?
In a compiler?
Yeah, for just a generic assembler.
Okay, so assemblers do not say how you should name your labels. So how you structure the names of your label is entirely up to you. So some people just like sequential numbers. So they go L1, L2, L3, L23, L24, and so on. They just keep going. Some people use the control structure as a part of the name, which makes it very long. Some people use abbreviations. For instance, you can say W for while, so your label names can be shorter. So it's entirely up to you. But the point is, you have to watch out and make sure that you do not reuse a label accidentally. And there's no easy way to get it done, because you can only mentally keep track of so many things. But when you name the labels in a very structured way, it helps a little bit. Yep.
So, what language would the compiler be written in if it was going to compile C?
That's a very good language. That's a very good question, because a compiler. Okay, if you think about it, and you say, well, I can write a compiler in C, then how does what is the programming language of the compiler that compiles your C compiler, right? So there's always that question. So the very first compiler has to be written in assembly. So there's no way around that particular problem. Yep.
But it's depending on hardware, right? Depending on the processor and what machine language instructions it has, right?
Yes. So the actual assembly code for the compiler depends on the architecture. But it doesn't negate the fact that the very first compiler has to be written in assembly. But to answer the question, who asked that question? Okay. So compilers these days are written in either Yak or Bison. Yak stands for yet another compiler. And Bison is kind of a similar animal to Yak. I'm not kidding. That's why they name those programs the way they do name those programs. So I'm not kidding. You would think that I'm kidding, but I'm not that inventive. Yak is yet another compiler. And then when you look up Bison, and it has reference to Yak has to be somewhere. So in POSIX mode, Bison is compatible with Yak, not the animal. So this is how they name your programs. Yep. There's also lame, L-A-M-E. Lame ain't MP3 encoder, which it is. Okay, you guys look at me and go like, really? Lame, okay. So here's lame. Lame ain't an MP3 encoder, but it is. And then there's GNU, G-N-U. GNU stands for GNU is not Unix. So what is GNU? GNU means GNU is not Unix. What is GNU? GNU means GNU is not Unix. It is an endless recursion. And there's wine, W-I-N-E. Wine is not an emulator, which it is. Okay, you guys don't need to know all of these things because you live in an era when these things are not really useful, right? There you go. Wine is not an emulator, which doesn't actually explain what wine is, but at the same time does explain what it is, right? Okay, so I think I have digressed. All right, so getting back to this program, okay? So this is the process. Is it likely that you would encounter a program like this complex in your homework assignments? Probably not. I cannot say 100% that is not the case, but I can say that it is unlikely because it makes it very difficult for me to grade. But the technique to do it, I'm hoping that you guys observe the technique itself. Not so much line by line, which translates to what, okay? But it's the technique. I only deal with one control structure at a time. Okay, I don't look at the whole program and do translation like from the first line to the last line. I jump around. I just deal with the outermost loop first. Get it done. Move on to the next level, move on to the next level, and so on. So are we good so far? Yes? Okay. So do you guys want to understand what your program does in the previous homework assignment? That big loop thingy? Okay. So let's go back and look at that program. And then we can put it into the simulator, run it, and look at the trace log and all kinds of good stuff. Okay, so let's see, that one is right here. Actually, that's not what I want. I want to do a preview. And let's go to question number 3 or 4. 4. Okay. So we have the code here. Copy. And put it into, put it here. Paste. There we go. Okay. So from what we have talked about today, can you reverse the process and tell me what is the actual control structure of this program? Now, what we have done today, okay, let me switch to the other notepad to look at this mess here. Look at this mess here. This is compiling. Compiling starts with something that is structured and turn it into something that is unstructured, flattened, okay? Now I'm trying to do the reverse, okay? I started with something that is completely flattened. Do you see a curly brace here to tell you something about the structure of the program? No. Well, but is there structure in this program? Yep, there's structure in this program. And now the question is, what is the structure of this program? If I were to convert this back into semi-C code, okay, to look at the control structure. One thing you can know for sure is this is initialization, right? A is ID, and B is ID. Okay, because LDI just does that. Yep, question? Nope, okay. So now we have a label L0. Out of nowhere, what does that tell you? It is a part of what? Well, we only have so many control structures, right? We have conditional statements, we have pre-checking loops, we have post-checking loops. So which one can you rule out right away because of the L0 preceding a bunch of code? It cannot be conditional. Okay? It can be post-checking, okay, but it cannot be conditional statement. So we know this is some kind of a loop begin, okay, begin loop of some kind. We don't know whether it's a while or do while, okay, at this point. But then you see this JMPI to done, and done is all the way down here. Oh, what is that reminding you of? It's a pre-checking loop, okay, because we're looking for a reason to get out. Okay, so if we're looking for a reason to get out, what is the reason to get out? The reason to get out is we do not do a JCI, Okay, so if I were to comment, okay, so let me comment on this one here. So we are somehow going to done, but the reason why we're going to done is B compared to C is something that causes me not to, that will lead me to go to done. So the question now is, what should I put here? Should I put less than, greater than, less than or equal to, greater than or equal to, not equal to? What should I put here? Well, if you think about it, if B is in fact less than C, I would have gone to continuation, right? So it's only when B is not less than C that I would go to done. So that means this is greater than or equal to. But wait, if greater than or equal to is the reason to get out of the loop, when we specify a while loop, we specify the condition to stay in the loop, right? So what is the condition to stay in the loop? When B is less than C. That's right. Okay. So that means, from here, we can now say while B is less than C, do the following. Where's the end of this loop? Well, where's done? Right here, right? This is the end of the while loop. We only have one while loop in this entire program, so I can just say while and while. Is that okay? So you use the conditional branches and the branching and the definition of the label to define the structure of your code. This is exactly the reverse of what we did earlier in the class. Okay? Okay, so what is inside here? I see more branching, right? So if I see more branching, that means there are more control structures here. Well, let's just make this a JCI here. Okay. What is the reason why I would go to label L1, and what kind of control structure are we talking about here? JCI go to L1, JMPI go to L2, but eventually they both converge at label L3. So we have a decision to make to go this way or to go that way, but both paths would merge at L3. Both paths will go back to L3. So what kind of control structure is this? It's a conditional statement with an else, okay? All right, so if I look at L1 as the then branch and L2 as the else branch, how would I put this? What is the condition? In other words, under what condition do we go to L1? If C is less than D, go to, then we have the then branch, right? And then the else branch is here. Okay? Nope, put it on the wrong place, sorry. Right here. This is the else. Well, what are we actually comparing? What do you think? So on line 10, what is the actual value of register C? It's whatever A is pointing to. Okay. So that means here, instead of using C, in C notation, I can just say whatever A is pointing to. And then here I can say whatever B is pointing to. So we are looking at whatever A is pointing to and what B is pointing to, and then use that to determine, should I go to the then branch or should I go to the else branch? Which impacts your counting, okay, when you're doing this homework assignment. So I know I'm running out of time, but when I go back to the beginning, this increment B is actually inside the loop here, and we are loading this into C in order to determine whether we should exit or not. So C really is not a particularly useful register, because all it is really doing is to represent the label and ID end, which is the end of an array. And then we also have an increment B at the beginning. Do you see this increment B here? And it is done before the comparison. So that means we have an auto increment at the beginning. There's an increment C somewhere. That's A and B. And then I copy A and B here. So increment A is down here. So after the end if, we have ++A to increment that pointer. So the two pointers are basically always one is always ahead of the other one, and we are comparing consecutive bytes of your student ID spelled backwards. That is what the program is doing. Okay? So I didn't really quite have time to run this code through and illustrate what happens when I paste it into the trace analyzer, but you can do it on your own. Okay? The trace analyzer is working. You just have to make sure that you re-download processor 0003.circ because I changed the locations of the output pins, and that changes the ordering of the output of Logisim. So you have to re-download it if you plan to use the trace analyzer. So we do have lab tonight, okay? The key is ABS, all lowercase for absolute value. ABS, which is also anti-lock break system.